Okay, so we're going to continue today discussing the uh, issues of electromagnetism and how they affect the structure of the atom. So we're doing what we would call a microscopic description of matter, and that's one of the challenges in chemistry is that sometimes it's referred to as a sort of triangle in that what we're learning, we're doing calculations, right? So there's a lot of math that we're doing, a lot of arithmetic. But then we also are looking at what's called a macroscopic description of matter, right? So when we talk about counting the number of moles of oxygen gas or looking at the pressure, calculating the pressure of a gas at a given volume and temperature, that's a macroscopic description of matter. We're just looking at the sort of bulk properties of something. But there's a third category, which is the microscopic description, which is equally important. And so the microscopic description is like, why do gases behave the way they do? Why do solids behave the way they do? And in order to explain that, we have to have an understanding of what the atoms themselves are doing. How are they behaving? And so that's really what we're getting into in this chapter is the structure of the atom and how that affects the properties of the atom. And then eventually, by extension, we'll look at how the properties of the atoms affect the properties of molecules. And then we would look at how the properties of molecules affect the property of large structures. Okay. So what we've done is we've said that one of the things we can do is we can use light as a way to study, to test, to probe matter, right? What we said was that if you have an atom, and in the previous examples, we just looked at the hydrogen atom. We didn't even look at any of the other elements. We didn't look at helium or lithium or anything. We just looked at the hydrogen atom. And we said that electromagnetic waves are waves, right? So that means that they have some vibrational property that can interact with the electrons of an atom, because the waves that we're looking at are electromagnetic in nature. So they create an electric field, they create a magnetic field. Those electromagnetic waves can essentially cause the electron, sort of an analogy, almost to cause it to vibrate from one state to another. So the Bohr model said that if the energy of the wave or the energy of the photon matches the energy difference between two states in the hydrogen atom, that photon can be absorbed by the atom and promote the electron to a higher level, which we call a transition. Okay. So in order for that to happen, the energy difference of the two states in the atom, so let's say this is state one and this is state two, that energy difference, delta E, which is E2 minus E1, has got to equal the energy of this wave, this photon. And if it does, there are other rules as well that we're not going to go into in this course. There's certain limits in terms of what can happen. But essentially, if that energy difference matches the energy of the photon's energy is transitioned into moving the electron from one state to another. Likewise, if the atom has an electron in a higher state, so let me put the electron in the third state. So if the electron is in the third state, it can spontaneously, meaning on its own, without any interaction with the environment around it, the electron can jump down to a lower level, undergo a transition. And then what will happen is a photon will be emitted by the atom. Okay, and so that excess energy of the electron being in the third state is converted into a photon. So this gives matter a way to transfer energy, right? Matter can absorb energy in the form of these photons, it can emit photons, release energy in terms of that as well. And so when we see a light bulb, essentially what's happening is all that excess electrical energy that we're putting in from the wall or from a battery is being converted into radiative energies. So the energy is being converted into electromagnetic waves. And the same is true for a star. A star is really, really hot. The electrons are moving to all these very high level states. They're dropping back down on their own spontaneously and emitting photons. And those photons are radiating out into space. Okay, so we now have, if you think about it, a real connection at the atomic level between matter, right? I mean, an atom is getting pretty fundamental. We're not talking about a big giant thing like a car. It's pretty complicated. We're talking about, you know, really the simplest form of matter that we interact with, which are atoms. That atom now, we have a way of explaining how it absorbs and how it transmits energy. And so that's through the form of electromagnetic waves. And even at room temperature, atoms are vibrating. They have kinetic energy. They have potential energy. They're radiating that energy just in forms that we can't see. We can't see infrared radiation. We can only see visible light, but at room temperature, they're emitting electromagnetic waves and absorbing electromagnetic waves. They're absorbing radiation. They're emitting radiation. If you take a piece of metal like aluminum foil, I see sometimes people will put aluminum foil on their windows in the summertime with the idea that somehow that's going to block the radiation coming into the room and cool their room off. And it turns out metals absorb radiation. It's actually not a very effective way of cooling your room because they actually absorb. The aluminum foil will absorb the radiation of the sun. And it's true, it will reflect some of it, about half of it, but the other half will get absorbed and then transmitted essentially as in the form of heat into the window and then into the room. So there you go. So what we're going to look at, so that was, you know, essentially this idea of transitions and energies of the atom. What we're going to look at today to start with is we're going to look at the next issue, the next stage of understanding. So looking at this Bohr model, Bohr essentially said this, right? He said that you've got these states. The electron is a particle. He looked at the electron as a particle, like a little planet, essentially. A fundamental particle, a particle that, as far as we can tell, cannot be divided into smaller particles. There is no way to take an electron and smash it into two electrons or two half electrons. It seems to be such a fundamental particle of the universe that it is indivisible. And the electron is in orbit. And then what can happen is an electromagnetic wave comes in, the electric field of the wave somehow interacts with the electric charge of the electron and gives it energy. And then the electron is now up in this higher orbit, and that's called a transition. And then spontaneously it can jump back down. And when that happens, it emits a photon, right? So Bohr didn't have a real good answer for why these particular orbits were stable. Why is it that this electron can just keep going around in a circle around the nucleus? It seems like maybe that's possible, except for the fact that it turns out in physics that any particle that has a charge, if its velocity is changing, it will radiate energy. Okay. So if you take an electron, you can say, well, maybe it's not really accelerating. Maybe it's going at the same speed. But it turns out circular motion is a form of acceleration. So remember, velocity is not just speed, not just how fast you're going, 20 or 30 miles an hour. It's the direction you're going. So if you change your direction, your velocity is changing. Your speed might not be changing, but your direction is changing. Your velocity is changing. And you can kind of, if you're in a car and you're doing a turn and you're moving at 30 miles an hour and you turn and you keep that speedometer at 30 miles an hour, you're going to feel an acceleration. Your body is going to start to fly off to the side and you're going to have to hold your body in there, right? You're feeling an acceleration. So what happens is when something is undergoing circular motion, its direction is constantly changing, right? You're changing your direction all the time if you're in a circle. So you're always accelerating in a circle, okay? So when a spacecraft is orbiting the Earth, it's always under some form of acceleration. And if you're accelerating and you're in a charged particle, which an electron is a charged particle, what you will do is you will radiate out energy. This is a well-known physical phenomenon. And if you radiate out energy, you are losing energy, so you will move closer to the nucleus. But since you're moving closer to the nucleus, your velocity is changing, so you will radiate more energy out into the environment until eventually the electron will spiral down into the nucleus. And that clearly doesn't happen. Atoms are stable. The electrons don't spiral down into the nucleus. They seem to be stable. So that means there's a need for an explanation as to why these specific orbits that Bohr came up with, why are they stable, you know? And he had no answer for that, right? And no one had any answer for that. No one was able to figure out why it is that in these states, the electron was somehow stable. So Bohr, what he tried to do was he tried to extend this theory to other elements like helium. Let's take the second most complicated element, or the second most simplest element, which is helium. 2 electrons in 1 nucleus, right? He could not, and the people working with him, could not develop a mathematical model of the helium atom that allowed them to calculate the spectrum of helium. So when helium emits different colors of light, which is often referred to as a fingerprint, they could not match up the lines like they could for the hydrogen atom. So he was able to calculate the hydrogen atom pretty effectively. But even the hydrogen atom had problems. It turns out that if you apply a magnetic field to the hydrogen atom, each line splits into 2 lines. So he tried to figure out, how can you explain that? How do you get 2 separate lines out of 1? The energies are different in some way. And in a sense, this is related to magnetic resonance imaging, the idea that these lines can be split by magnetic fields. And they couldn't come up with an explanation for that as well. So lots of problems with the Bohr model. There are other problems that I won't go into. But the point was that they realized pretty quickly that this was not going to work. It could explain some aspect of atomic behavior, but not, by no means, the complete explanation for what was going on. So people were kind of struggling to figure this stuff out for a while. They tried all kinds of mathematical models, but they were at a logjam. They really couldn't figure out what was going on until this man from France, deBroglie, Louis deBroglie. I can't pronounce his name right, but whatever. Very few Americans can. Essentially, he came up with this idea. He had a hypothesis, which he was not able to test himself, but he was able to kind of think about things and look at what people were studying at the time. So he was reviewing the literature. And he came up with this very interesting idea, which was that if we think about the photon, which is pure energy. A photon is just it's energy that moves at the speed of light. We actually have 2 ways of explaining it. One way is that it behaves like a wave. It undergoes this phenomenon called diffraction. It reflects, it refracts. These are all properties of waves. But in some sense, Einstein was able to show that the photon is also a little packet of energy. Right? So it's a packet of energy. So it's a wave. And remember, waves spread out, right? Like if I say, hey, where is the wave when you look out at the ocean? You can't tell me where the wave is. You can say, oh, it's over that region of space. It spreads out over that space. But you cannot locate the wave specifically, right? There is no one location of the wave. It's an extensive property. Or phenomenon. But a particle is something that you can locate, right? So if I say, where is that car? Oh, it's right there. Or where is that atom? It's right there. Where's that molecule? It's right there. So a photon is two different things at the same time. It's a wave, it has vibrational properties, it has a wavelength, a frequency, and amplitude, but it's also a particle. It's also this object that moves through space and you can locate anytime you want to, okay? So deBroglie said, okay, since we're starting to look at things that are getting really, really, really small, that's a different world. How do we know that the physics of the small world is the same as the physics of our world, right? So if I'm moving as a human being with something that's a meter long or 2 meters long or 2 inches long, do we expect that object to behave the same way that something that is 10 to the minus 9 meters, right? Do we expect something that's really large to behave the same way? So they did know at that time period, based on the work of Einstein, or they were finding out right at that time period, that once you get up to things that are really, really large and really, really massive, they behave differently, right? Einstein predicted that if you had a star that was heavy enough, it might actually be able to squeeze down space itself to such a point that you create a black hole and nothing can escape it. You're essentially puncturing space itself, right? So they were starting to realize that at the very large scale, things didn't behave like they do on our scale. So maybe the same is true when you get to the microscopic world. Maybe it's the case that you cannot really have a planet like ours that's the size of an atom, that the physics of the atom is so different that you couldn't have little people that are really, really tiny, okay? And so he proposed the following idea, which is that a electron, which is a tiny particle, is actually a particle, but it's also a wave. It has properties of both. And we call this wave particle duality, wave particle duality. Okay, duality is both. And so under some conditions, the argument goes, the electron will behave just like a particle, like a little bullet, right? So old television sets, old computer monitors work on that principle. Essentially what you do is you have a big piece of glass, you evacuate it, you pull the air out, you put some pieces of wires in it that are some distance apart, and you apply really large voltages, hundreds of volts, and the electrons will boil off one of the wires, fly to the other wire through space, just like little bullets. And they called them electron guns. An old television set, if you talk to a technician, they would say, oh, that's the electron gun, because it's boiling off these electrons at high temperature and they're flying through space like little bullets. So there's definitely a particle-like property of the electron. And all of our models that we've talked about thus far, you know, counting electrons, redox reactions where you write the electron as an E negative, a little particle that jumps from one atom to another, counting the number of particles in the nucleus and around it. All of that is based on this idea of a particle electron. In fact, when we get to the next chapter, when we get to chapter 7 and 8, we'll start looking at the electron as particle. However, once you start looking at some of the more interesting experiments, what you find is it turns out the electron also has wave-like properties. It undergoes this phenomenon called diffraction, where essentially if you take an electron and you put it through a really, really small hole, a tiny little hole, it will spread out like a wave, okay? And so today, we actually have a technology called scanning tunneling microscopy. It's a way to image really, really small things, even down to the level of molecules. And it is based on the idea that the electron is a wave. And there's also something called scanning electron microscopy, which again is based on the idea that the electron is a wave. It has wave-like properties. And this is something that Bohr and his colleagues had not kind of considered. deBroglie was the one who came up with this idea. Initially, it was rejected by the community. until an experiment was done not long after his hypothesis. And the experiment showed that, in fact, the electron does behave like a wave. It spreads out over space just like a wave. It undergoes something called constructive and destructive interference. And that was definitely a property of waves. You can do it with sound waves. You can do it with water waves. You can do it with light. But it turns out it also works with electrons, and not just electrons. It works with protons. It works with neutrons. It works with hydrogen atoms. Today's physicists will study the largest molecules they can that still have this wave-like behavior. So if we look at things like calculators, they do not behave like waves. If we look at things like cars, they do not behave like waves. However, very small particles, small molecules, up to around 20 or 30 or 40 atoms will behave somewhat like waves, and electrons definitely behave like waves, and protons as well. So deBroglie was correct.
Back like that too?
I'm sorry, what?
Do they bounce back in the way that like sound waves would too? You know, like motion sensors, for example, that will bounce sound waves. Can you
Yeah.
so electrons that behave like waves, they will bounce back, and you can analyze that as well?
Yeah, and it turns out they also seem to split into two. So they seem to go through, if they go through a hole and then you have two holes behind them, part of the electron will go through one hole and the other part will go through the other hole. So they're splitting just like a wave. So if you take a liquid and you put things floating on the surface of the water, like little pieces of paper, and then you drop something in the middle, the wave will go out, and the waves will sort of bend around and split around the things that are floating on the surface, and then recombine after they come back, after they get to the outside. So it turns out electrons do the same thing. And so, yeah, they have all those kinds of properties. It's very interesting. So if that's true, which it seems to be, we're pretty convinced now that electrons have that behavior, that means that we need to apply a very different set of mathematics to them. So when we think about an object moving, we talk about velocity. We talk about trajectory, right? So like if you're putting a rocket into space, you know, you talk about its velocity, you talk about time, you talk about position, X, Y, Z, and we talk about what are called trajectories, and you can put things into orbit that way. There's a particular type of mathematics, Newtonian mechanics, we call that, right? If we're talking about waves, it's a very different set of mathematics. There's some similarities. We're still measuring time and distance and all of that. But we talk about very different aspects of it. We talk about amplitude, we talk about wavelength, we talk about frequency. Those properties are unique to waves. And so that means we have to have mathematics for the electron that differs from what we expected it to be. And so in a sense, it's quite remarkable that Bohr was able to at least predict the spectrum of hydrogen based on Newtonian mechanics. It turns out that the hydrogen atom is such a simple object, it's such a simple particle, it's one electron with one proton, that to some extent, Newtonian mechanics can explain it. But once we start looking at more complicated atoms that have more than one electron, even two, that mechanics breaks down. So essentially what can happen in mathematics is that you can have two different mathematical models that both work for something that's really simple. But as the problem becomes more complicated, one of them may quit working, but the other one will continue to work. And that's essentially what happened here. So let me give you the equation that we're going to use to begin with, that deBroglie came up with. And this is for the wavelength of a atomic particle or subatomic particle. So it could be an electron. We're going to do it mainly for, or chemists mainly do it for electrons, but we can also do it for atoms. Okay. And it's the wavelength of one of these, what we'll call a matter wave. So this is for matter waves. So this is not for the photon. Remember, the photon has its own equation. And I'll point that out in a moment. So these are for matter. And the equation here for matter waves is relatively simple. It's h over p is the wavelength. So remember, lambda is our symbol for wavelength. Okay, and the wavelength is in meters or nanometers or millimeters, some measure of length, right? And the wavelength is in some sense a measure of the size of the wave, not the height of the wave, not how intense it is, but how big it is. Like, how big is this wave? Okay, so there's our wavelength. And typically we measure it by measuring just how far it is on the x-axis, right? This is the x-axis. How far it is from one peak to the next peak. And that's not the only way to measure it, but that's the typically way we explain it, okay? So what does this say? It says that if we're talking about these matter waves, so that'd be electrons or atoms or protons or neutrons, the wavelength, the size of this wave, is equal to this ratio. And this ratio, this is called Planck's constant, right? And that was 6.626 times 10 to the negative 34 joule seconds. Remember, it had energy and time units in it because it had to relate the energy of a photon to its wavelength or to its frequency, okay? Now down here, this is P, which is called linear momentum. This is the symbol that we use for momentum, okay? Now, what is momentum? Momentum is, in a sense, a measure of the amount of motion something has. So it's a measure of how fast it's moving, but also how much mass it has. And so the linear momentum, P, is equal to the mass of the object times its speed. So I'll use V for velocity. It's technically it's velocity. We're just going to use speed, but technically it's velocity. So mass times velocity. So this is momentum is something that Newton worked with. And so we use it, we kind of have a sense in our everyday lives about momentum. We realize that if we see a marble rolling down a road toward us, that, you know, we don't need to be too careful about that, even though it might be rolling down the hill pretty fast. We recognize it doesn't have very much mass, so it's not that dangerous to us unless we step on it while we're walking or something. If a bowling ball is rolling down the hill, we know, oh, we probably want to get out of the way of that bowling ball, right? Because it has a lot of mass and it has a large velocity. So an object that has a large mass and a large velocity has a lot of momentum. Now, one aspect of momentum is that it transfers, right? So if I get hit by a car, the car will transfer momentum. It has mass and velocity to me. Technically, when it hits me, it slows down because it's transferring some of that momentum to me. Its mass doesn't change, so its velocity will decrease. This is this idea of conservation of momentum. But since the car is so massive and it may be moving quickly, it may have very large velocity, faster than I can run, it has a lot of momentum to transfer. So even if it only transfers 1% of its momentum, that might be enough to cause me to move at a very high speed, a dangerous speed, okay? So what this says is the wavelength of an electron is equal to this Planck's constant. And he got this equation from Einstein's work, divided by the linear momentum, divided by mv, okay? Close this off here. And so here's a way to kind of visualize this. So you got the nucleus at the center of the atom. And now what he's saying is you've got this something, which we call an electron, which has a negative charge. And what he said is that it's vibrating in and out. It's a wave that's vibrating in and out. And so you can maybe change the wavelength. There we go. I'm going to put the nucleus here at the center. So this, so that's the nucleus, and then this is the electron wave vibrating. So you can change the wavelength of the electron, but essentially what he said was that you had to have an integer number of complete vibrations around the nucleus for it to be stable. So it's sort of like some waves are stable and some are not. And so if you don't have an integer number, 1, 2, 3 wavelengths, some number of cycles of the wave around the nucleus, it'll be unstable and dissolve, So only some wavelengths are allowed. And what that does is it then allows you to start looking at the calculations of, oh, you got this one wavelength, you got a different wavelength for a different orbit, you got a different wavelength for a different orbit. But it's, in some sense, it's a vibration. In particular, it's what's called a standing wave. A standing wave is a type of wave. It's actually a combination of waves. If you take a string and you vibrate it, the wave will transmit down one side. When you start going up and down on one side, it'll do that. Okay, and then it'll bounce back and start going back the other direction, right? So what happens is those two waves will interact with each other and they'll add, and then you'll get a wave. It looks different than each wave going back and forth. It'll look like a wave that's standing. It's not really moving, but it is actually, there's motion in both directions, and those two are adding together to give you the perception that the wave is not moving. And, guitar strings work on that principle. Drum vibrations work on that principle. You've got on a guitar or a violin, you've got two ends. You pluck the string, energy goes back and forth in both directions. Those two vibrations interact with each other, and then you end up with a wave that is standing. And that's the wave that we experience. We experience the sound wave as that standing wave coming out of the guitar. It also works for drums. Drums are a similar type of phenomenon. It's just that a guitar drum is two dimensions. It's a membrane as opposed to a string. A string is a one-dimensional phenomenon. A membrane is two-dimensional. So for deBroglie, the electron is three-dimensional. It's not two-dimensional or one. The atom is not really a circle. It's a sphere. So these vibrations are three-dimensional waves that are vibrating in and out of space. Okay. And what it says here is that the wavelength of this wave, of the standing wave, it depends on this constant, that's fine. But it also depends on the mass of the particle. So an electron has a mass. In fact, the electron mass is approximately 9.109 times 10 to the minus 31 kilograms. We're going to use the MKS system for these calculations. You want to use kilograms for mass. So it's a tiny mass, but that mass affects the wavelength. So if an electron had a different mass and it was moving at the same velocity, it would have a different wavelength, but also the speed, the velocity. The speed of the electron. Now, what does that mean, the speed of the electron? Well, as we're saying, the electron has wave-particle duality. So it is true that it is a wave vibrating around the nucleus, but at the same time, it is a particle moving around the nucleus. It's both. And so that's very difficult for the human mind to understand because we're talking about two opposite concepts. They're not exactly opposites, but they're very different from each other. Something that's vibrating, a wave that's standing, we're saying it's that, but we're also saying it's something that's moving around, right? So that's something that has really, humans struggle with now. Even though this physics appears to be correct, the microscopic world behaves very differently than the macroscopic world. It's difficult for our brains that were evolved on the plains of Africa to be able to, hunt and gather foods. It's very hard for our brains to kind of understand this. So that's why we need these abstract concepts like mathematics that explain these things, because our everyday experiences don't explain these things. Okay. So mass and velocity, those are the two variables that determine the wavelength of this matter wave, this electron or atom, if we wanted to look at an atom. And as I said, it turns out that the electron has a behavior that's very similar to other types of waves. So what you can do is you can make the electron go at a particular speed, and it has, well, the mass you can't change of an electron, but you can make it go at a particular speed. H is a constant, but you can make it go at a speed so that the wavelength turns out to be the same as some of our electromagnetic waves, visible light, ultraviolet, X-rays, and all of that kind of thing. So X-ray diffraction, which is a method of really measuring the distances between atoms in a structure, allows you to really do analysis to see how, if you have impurities. So if you're making a metal that, you know, is going to be used for something really important and you want it to have no defects, you can use X-rays to measure that. But now you can also use electrons, because electrons, you can match their speeds so that they have the same wavelength as X-rays. It gives you another type of technique to look at the structure of matter. Okay, so matter waves. What I want to do is I want to show you an example problem here that's on Alex. There's only one in this section, but it's a really pretty interesting problem, but it's also kind of tricky. Okay, so let me stop share here and bring this one up. Okay, now this type of problem has 4 different questions, which are really the same question, just different numbers. All they're doing is they're changing the numbers. And it says in here, so we're trying to understand the meaning of the de Broglie wavelength. It says, imagine an alternate universe where the value of the Planck constant is 6.626. So that's the value I gave you. But notice now, it's not 10 to the negative 34 as it is in our universe. It's 10 to the negative 36 joule seconds. So it's a different value. So in physics today, there is this discussion going on about the possibility that there are other universes and that our universe is just one that popped into existence out of another one, and that they come in and out of existence. And so there are many and infinite, perhaps, in other universes. So one question is, if you have another universe, does it have to have the same values of physical constants that we have? There's no necessarily good argument for that being the case. So imagine that we had a different value of H. How would that change the behavior of matter? So we have this idea of speed of light. That's a constant. There's a charge of an electron that is constant. There's the mass of an electron that's a constant. As far as we know, the mass of an electron is the same today as it was 14 billion years ago. We don't know that for a fact, but that's one of our assumptions. We believe the value of the Planck constant is the same and will be the same until the end of the universe. But suppose it weren't, suppose it were a different value. How would that change the behavior of things? So in this question, it says, in that universe, which of the following objects would require quantum mechanics to describe? That is, would show both particle and wave properties. And which objects would behave like everyday objects, the macroscopic objects that we deal with, and be adequately described by classical mechanics? Now, I can be fooled on occasion into thinking that the things I deal with on a daily basis are quantum mechanical in nature. So for example, I might pick something up and then it just seems to mysteriously go through my hand and fall on the floor. Now that's probably just because my brain stopped for a few milliseconds and I just sort of dropped it. I lost muscle control. But imagine if a calculator behaved like a quantum mechanical particle, like a wave. The thing about a wave is that it spreads out and it can move in that way. So in theory, if this were a quantum mechanical particle, sometimes when you pick it up, it would just go right through your hand and then fall to the ground, right? Sometimes if it were on the ground, it would sometimes move up through space and then be in your hand. So we exist in a world where that doesn't happen. If it did happen, it would be a very different kind of world. We would have to adapt to that in some way. I'm not sure we could adapt to that in some way. Things would be pretty unpredictable. So there is a certain amount of lack of prediction, right? And this is the reason, this is the primary reason that physicists were really shy of accepting quantum mechanics back in the 1900s. Even today, there are physicists that say there must be some other physics behind it because it just doesn't make any sense. How can you have this uncertainty? Einstein was one of them. He didn't really believe that this was the end-all physics that would explain matter. But as far as we know, it does seem to work. And so what you do in this particular problem is they're going to give you an object. So here's a turtle that has a mass of 760 grams. So they're giving you the mass of the turtle. And then they're giving you the size. So in these problems, they're going to give you the size of it, right? So it's just one dimension. We're not worrying about like how tall the turtle. They're just saying how big it is. This is how big it is. This long, it's this long, or it's that long, right? And it's moving, right? So why is it moving? It's moving because we're going to do this deBroglie calculation. In the deBroglie calculation, to calculate its wavelength, we need to know the mass. We need to know the velocity, right? So that's why they're giving you the mass of the object, m. They're giving you the velocity object, v. H is a constant. We know that value, but we got to use this constant up here because for this particular problem, it's a different value of h. Okay, so they're giving you MV. Now, notice they're going to, one of the things about this problem is they're going to really test your SI prefix competency. So they're giving you the speed in centimeters per second, which why? Because turtles move very slowly. They don't go in meters per second, they go in centimeters per second. They're slow. So we do want to use MKS units. We want to use meters for length, kilograms for mass, and seconds for time, MKS. So this is not in kilograms, it's in grams. So we're going to need to put that in kilograms. This is not in meters, it's in centimeters. So we're going to want to put that in meters. Actually, interestingly enough, this is actually the CGS system. Chemists used to use the CGS system, which is grams for G and then centimeters for length. So this would, if we actually used, instead of using joules, we used ergs and different units, this would actually work out pretty nicely. But you're gonna, for us, we're gonna use the MKS. So you gotta kind of do all the conversions. Here's another one, a buckyball. Now a buckyball is a small molecule that was first discovered in the 1980s with a lot of fanfare. People were very excited to find this. It turns out if you take pencil lead, which is graphite, and you burn it with very little oxygen, what will happen is you'll get these little balls, these tiny little balls that look like soccer balls, and there's 60 carbon atoms, and they make this sort of like a net that folds over on itself into little balls. So for a long time, for a while, people were very excited about this. They thought they could make new materials out of it and really kind of changed consumer products based on it. It didn't really pan out the way they had hoped, but they are interesting molecules. So the buckyball has a mass of 10 to the minus 21 grams. So again, there's your mass. It's in grams, not kilograms. It's very small because it's a molecule. Now the size is really small, 10, nano is 10 to the minus 9. So again, very small. And then it's moving at 13 meters per second. So you just want to tell for all these particles whether they're classical or quantum. So how do you do that? Well, it really comes down to the wavelength. So the main kind of evaluation you do for this is if the wavelength of this object is about the same as the size or larger. Okay, so for example, this size is 29 centimeters. If you got a wavelength of 29 centimeters or more, 100 centimeters or 1,000 centimeters, it would behave like a quantum particle. It would behave like a wave. If, on the other hand, the wavelength you get, the lambda, is smaller than 29 centimeters, like 1 centimeter or 10 to the minus 5 centimeters, then it would behave like a classical particle. So I'm not going to go, well, yeah, Here's an iceberg. So notice an iceberg. It turns out a human, if you do the calculations, very simple, right? A person weighs about 70 kilograms and they're walking. So they're moving maybe 5 meters per second or 3 meters per second. If you do that calculation, it turns out our wavelength is like 10 to the negative 31 meters. It's tiny. And so that's so much smaller. The wavelength is so much smaller. It's so localized that we don't really behave like a wave. We behave like a classical particle. Okay. So hopefully when you do these problems, they won't give you one where it's like, oh yeah, the size is 29 centimeters and the wavelength is 28 centimeters. I don't think they would be that kind of mean, because if they're about the same, it's going to have quantum relationships. So most of the time, it's either going to be the wavelength is bigger than the size, but it'll be bigger by a lot, or about the same, or it'll be much smaller. And if it's a much smaller wavelength, then it's going to be a classical particle. Okay. So let's go through this one. I'm going to do at least a couple of these. This one, that's not a very big difference, 10 to the negative 34 versus 10 to the negative 36. So I'm going to do the following. I'm going to show another, and I want to see one where they make H quite a bit different. So see this one right here, 10 to the minus 16. That's a big difference, right? It's not 100 times bigger. It's now 10 to the 18th times bigger, right? It's 1 followed by 18 zeros. So that's a big difference right there. So this one's a little different, but I want to look at one of those big differences. Okay. So same question though. So here's an alpha particle. So an alpha particle, just so you know, is a radioactive particle. It's something that comes out of a nuclear decay. We talk about it in the next course. Some elements are unstable and they emit these alpha particles. They're subatomic particles. They're really essentially helium atoms. And they're giving you the mass, they're giving you the size, and then they're giving you the velocity, and you're just going to answer which one it is. Okay. So let me do this one. So I'm going to bring this up over here, and then I'll just write the numbers down over here on the side. So here we're going to do the alpha particle. Which is really a helium nucleus. It's kind of cool. Some atoms will just barf up little atoms, little helium atoms. That's where our helium comes from. It's from uranium doing that. Okay, so here, H is equal to 6.626 times 10 to the negative 16 joule seconds. And then they give us the issue, the variables. The mass is 6.6 times 10 to the minus 27 kilograms. The size is 8.0 times 10 to the minus 15 meters. And then the velocity, it's moving at 13 kilometers per second. Okay. So let's go through it. So what you do is you calculate H over MV. And you just want to make sure you're in the MKS system. So that means meters, kilograms, and seconds. Okay. Now, it looks to me like most of these problems, they give you the velocity per second. So that's going to be in seconds. So that's not an issue. The issue is the mass in kilograms. Well, here it is. That's in kilograms. That's good. So we don't have to do that conversion. The size is in meters. That's pretty cool. So they gave us that in meters. The one thing they didn't give us in meters is here. Here's kilometers per second. So what I'm going to do is I'm going to change the velocity to meters per second. KMS, right? So kilos 1,000. So 1,000 meters is a kilometer. And so you get 13,000 meters per second, right? Your kilometers cancel. So there we go. So that's actually, this one's not too bad because they put everything in there except for the velocity in the MKS system. So now we can make the comparison. So what you're going to do is you're going to calculate lambda. So 6.626 times 10 to the minus 16 joule seconds. Divide that by the mass, which is 6.6 times 10 to the minus 27 kilograms. And then the velocity is 13,000. Moving fast. 13,000. What is this? Oh, it's an alpha. Yeah, it's an alpha particle. It's moving really fast. Okay. Luckily, alpha particles, even if they're moving fast, they can't really get through your skin. The skin is pretty protective for alpha particles, so it'll just stop on your clothing. Will even stop them. Gamma rays are much more dangerous. So 6.626 times 10 to the minus 16. See, by habit, I went to minus 34. You have to be careful. 6.626 times 10 to the minus 16 divided by 6.6 times 10 to the minus 27 divided by 13,000. Okay, wow, look at that wavelength. So the wavelength is 7. I'm not even going to do significant digits. 7.7 times 10 to the 246. Gigantic. Now, what that means is the following. I'm going to give you a little kind of analogy here. So here's a person, right? A person is, how tall is a person? 1.6 meters. That's a nice average value, 1.6 meters. So the idea is if the wave is longer, as long or longer than the object will work as a quantum. Right? So here, look how big that wave is. The wave is much bigger than the person, than the physical size. That means that person will behave like a wave. That person will be like spread out across that, and it'd be kind of cool. You'd be like a great dancer. You'd be flowing through the walls and stuff like that. You'd be able to split into two, that kind of recombine. So this is an extreme example because the alpha particle behaves like a quantum particle in our universe. It's subatomic, it's really tiny. So it behaves like a quantum mechanical particle. But with this big value of h, it's even more so. It's very quantum. It's very much like a wave. So the wave here is gigantic. It's millions of meters, which is thousands of miles across. The size of the object is tiny, right? So here, the lambda is much greater than the size. So it's going to behave like a quantum particle. Okay, so that one's easy. It's the same as it is in our universe. But let's look at another one in here. The second one is a virus. So this is kind of interesting, a virus, right? So, okay, what kind of virus? Well, we'll use that one they use in biology, the one that attacks bacteria, right? So that we don't have to deal with one that attacks us. So again, we're going to use h as 6.626 times 10 to the minus 16 joule seconds. We're using this alternate universe. And, sorry, the mass is not very big for a virus, right? It's 3.5 times 10 to the minus 17 grams. 300, so here's our size. 310 nanometers wide, and then moving, so your velocity is 1.90 micrometers. Why so low? Well, it's a virus. They can't move that fast. I mean, they can move through snot, right? They move pretty fast through a sneeze. But if they're inside a cell or inside a body, they move pretty slowly, right? At least on our scale. So only in micrometers per second. So in this particular problem, now we get to the dimensional analysis because this is not in kilograms, and this is not in meters, and this is not in meters. So for this one, we're going to have to do a lot of conversions, okay? MKS. So let's take our 3.5 times 10 to the minus 17 grams, and we're going to put it into kilograms. So a kilogram is 1,000 grams. Right? So kilogram to I'm sorry, gram to kilogram. We're going to divide by 1,000. So 3.5 times 10 to the minus 20 kilograms, right? Let's make it smaller. So there's our mass. Let's do our size. So that's M. So the size is 310 nanometer. Now, you know, the nanometer is 10 to the minus 9 meters. So 1 times 10 to the minus 9 meters is a nanometer. Okay, so that's 3.10 times 10 to the minus 7 meters. So there's our nanometers gone. So now we've got that. That's our size. Okay, that's not the wavelength, right? That's the size of the object, the physical size that we consider, what we consider physical. So once you start talking about quantum mechanics, the idea of physical size no longer really has the same meaning. It's not clear what physical size means. The physical size of a wave is, I guess, its wavelength, but that's only a measure of it, right? It's macroscopic world where we talk about the size of something. The velocity. 1.90 micrometers per second. So we got to get rid of the micro. Micro is 10 to the minus 6. So, and we're doing meters, right? So 1 times 10 to the minus 6 meters is 1 micrometer. Sometimes referred to as a micron. If you see micron, that's a micrometer. Micrometers are gone. And then you have 1.90 times 10 to the minus 6 meters, and that is the velocity. See, I was going to call it the wavelength because the micrometers is length, but no, it's per second, so that's your velocity. Okay, so we got the size. We're going to compare the size to the wavelength. So we calculate wavelength, h over mv. The textbook by Burge uses a U for velocity, and it did that in gases as well, but most people use a V for velocity. 6.626 times 10 to the minus 16 joule seconds. We're going to divide that by the mass, which is right here, 3.50 times 10 to the minus 20 kilograms. And then we're going to divide that by the velocity, which is 1.90 times 10 to the minus 6 meters per second. Sorry, I forgot our seconds here. Okay, I'm going to talk about the units in a moment, because if you go through the units, it might be confusing. So let's see what we get. 6.626 times 10 to the minus 16. Divided by 3.5 times 10 to the minus 20, divided by 1.9 times 10 to the minus 6. And again, you get this gigantic, it's 9.96 times 10 to the 9 meters. Well, that's much larger, right? Lambda is larger than the size. And again, if the wavelength is larger than what you think the physical size is, it's going to behave like a quantum particle. Okay. And so that will definitely be quantum. Now, in our universe, the virus doesn't behave like a quantum particle. A virus is too big to behave like a quantum particle. It's not the size of a cell. But even so, there are thousands or tens of thousands or hundreds of thousands, actually probably millions, right? Even a simple virus has millions of atoms. It will behave like a classical particle. You can't really get it to behave like a wave. And so in that universe, however, it will behave like a wave, very much like a wave, because the size of the wavelength is so much larger than the size. Right? Now, I want to talk a little bit about units, because if you look at it, and I didn't really talk about this, these units don't seem to work out. It doesn't look like there's anything you can cancel here. In fact, you can't cancel the seconds. You know, you got seconds here and you got them down there, but they're in the denominator there. It's really S over 1 divided by 1 over S, which would really be S squared. So how do you deal with that? How do we deal with these units? I'm claiming the units are in meters, so I want to prove to you that that's the case. So the units in the numerator are joules times seconds And then the units in the denominator are in kilograms and then meters per second. Doesn't seem, but remember, what's a joule? A joule is a kilogram times a meter squared over a second squared. So in the joule, you have kilograms and meters and seconds. So let's substitute that in there. It's kilograms, meters squared per second squared. There's your joule, times seconds, right? Because you got the seconds here, divided by kilograms, and then meters divided by seconds. So now here's what happens. This second right here cancels with one of those. So that becomes a 1. And then you've got this down here and this down here. Now they're both in the denominator, right? Now they cancel. So now those are gone right there. Then you've got kilograms divided by kilograms, and then you've got meters squared over meters. Well, one of these cancels with that one, so you're left with meters. And so it does work out. Okay, so that particular equation under the MKS system gives you meters, and that's what our answer will be. Okay, so have fun with that one. I don't think they actually ask you to put the numbers in, but you got to do the calculation to see whether it's classical or quantum. And again, if the wavelength you get is larger than the size, it's going to be quantum. If the wavelength is less than, then it's going to behave like a classical particle. Okay, so that was not a lot that we went through. We really just went through one topic there and one type of problem, but it's an important one, because what it does is it sets the stage for the rest of the chapter, which is we are now, for a while at least, going to start treating the electron as a wave as opposed to a particle. And that is going to lead to a whole new set of rules over how we deal with electrons. And by the end of the chapter, we're going to be doing electron configurations, placing the electrons in the atom in particular shells and subshells and orbitals and all of that. And that is all based on the principle that the electron is behaving like a wave. Okay, it's called the Schrodinger equation. So tomorrow, what we'll do is we'll look at the Heisenberg uncertainty principle, and which is an important part of quantum mechanics. And then we'll start looking at putting these electrons into these spaces, these regions of spaces that are called orbitals. You maybe have heard of orbitals. You've maybe in biology, you've heard of shells and subshells. We're going to look at all of that kind of stuff from the perspective of quantum mechanics and get a very deep understanding of what's going on there. Okay.
So the bigger the constant, basically the bigger the wave, and at some point it is, it's less and less significant, the actual size or speed of the object. So really large. Okay.
Yeah, the bigger, that's a good point. The bigger the constant is proportional to the wavelength. So the bigger the constant, the bigger the wavelength, which means the wave is spreading out. At some point, it becomes so big, it's bigger than the size of the object. And once it gets bigger than the size of the object no longer behaves like a classical particle. It behaves like a quantum mechanical particle. Exactly. It's a good way to look at it. Okay. Now, obviously, you can play around with the masses, and you can play around with the velocity is, but you're right. The main thing is that size of the constant. And in our universe, that constant is so tiny, 10 to the negative 34, that everything we deal with, from the size of a star to the size of a planet to the size of a virus, do not behave quantum mechanically. Only
so if you want to study something that's extremely small and you want to study it on a classical level, can you make it move like really, really, really fast, and that will decrease the size of its wavelength, and then it'll behave more like something that we're used to seeing?
Yeah, you can. And that's essentially what they do when they want to make these particles that are particular, like add molecules. If they want to make a molecule go back and forth, you can do that. So you have some wiggle room with that to play with experimentally. However, there's the issue is, first of all, you can't change the mass of an object. We don't have a technology that can change the mass of something.
Right, you
Right?
can only change the velocity.
Star Wars, they can change the mass of something, and Star Trek, they can do that. We can't do that. We don't have an understanding of mass in that way. But you can change the velocity of something. But there's a problem with that, and that is based on Einstein's work, which is that the faster an object moves, the heavier it becomes. And so this is really the reason, the primary reason, that building machines that could fly to other star systems really fast, we can't really do that. The speed limit is the speed of light, 3 times 10 to the 8th meters per second. But once you get up to about half the speed of light, the mass of the object becomes significantly heavier. That means you have to use more energy to make it go faster because it's heavier, which makes it heavier. And the faster, and so what happens is, by the time you get up to about 95% the speed of light, the object weighs so much heavier than it did before, you don't have enough energy to make it go any faster. And so the same is true here. There are limits, like how fast can you make these objects go? Well, they do have particle accelerators that can make atoms go really fast, but they don't have particle accelerators to make, you know, even a virus go really fast, because to make it go really fast, you need too much energy to make it happen. Plus, it'll fall apart. A virus
is also like relatively big, like in our universe. It doesn't, like, it's a classical object. It's pretty big.
Yeah, it's pretty big. But if you wanted to change its velocity to something really, really high, it'll fall apart. It'll just break apart. You know, the atoms will start flying apart. So, you know, we also run into this issue that there's forces that hold molecules together. And at some point, when the velocities are high enough, the energy required to make that happen just causes the molecule to fall apart. They just can't stay together. So there are like really kind of serious limits in terms of what we can do in terms of varying these things. You can make things go slow, but you can't really make them go fast if they're bigger. Cool.
Cool.